Okay, so this is the video lesson for 4.4 notes, and today we're going to kind of tie up some loose ends with some logs and also solve some equations, solving for x, both with exponential and logarithmic functions. Okay, so first let's go over the change of base formula. You learned this last year, but what this does is it'll take a log of any base and allow you to do a calculation or write an equivalent statement. There's a lot of uses, and we'll see some of those in this lesson. So if you have log of base b of x, okay, that is equivalent to log of x over log of b for any base, really. These, I've written them with the common log, but you could use any base here. Okay, you could even use natural log, and in fact, this is probably what we're going to use the most. All right, and this is what you'll see mostly in calculus. Okay, so now let's think about what log base 2 of 10 is. Now, you don't have a log base 2 in your calculator, so we're going to have to use change of base. There is a program in your calculator. We're not going to use that. It's much easier just to use the change of base formula, and it's a good practice anyway. So there's a couple of different ways we could write this. We could write this as log of 10. By the way, what is log of 10? That's 1 over log of 2. Okay, we could also write this as the natural log of 10 over the natural log of 2. And if you were, all three of these are equivalent statements, and if you were working with this and not, like let's say on a non-calculator portion, any of these statements would be fine. We'd probably use the natural log the most, or just this simplified log. We probably wouldn't use the common log. Okay, so I want to show you how this works in your calculator. But by the way, let's estimate what this is about. So we know that 2 cubed is 8. So I know it's somewhere between 3 and 4. Okay, 2 cubed is 8, 2 to the 4th power is 16, so it's somewhere between 3 and 4. We can estimate just by doing simple powers like that. Okay, so let's use the calculator to find it exactly. And so, like I said, you can do log of 10 divided by log of 2. The base always is the denominator log. Okay, and we saw that we get a number between 3 and 4. Now let's use natural log. So we have this button here for natural log, remember? And divided by natural log of 2. You don't want to switch it up and use log here and natural log here. Okay, and you get the exact same number, exact same. Okay, so there you go. That's how you use that. That's how if you want to get an approximate answer. And you would always want to round to 3 decimal places. So in this case, this would be approximately 3.322. Did I write that down right? Let me just double it. Yeah, 3.322. Okay. And we use these for approximate. You did this a lot in geometry where you had an approximate answer and an exact answer. With logs, it really depends. Sometimes in an application you want an approximate answer. Sometimes you want an exact value, and all of these are exact. Okay. So let's talk about how we can use this for graphs. All right, if I ask you to graph y equals log base 3 of x, well, you know that this is basically the parent function. All right, the base of the log does matter, but some things that aren't going to change are this vertical asymptote at x equals 0 and this point right here at 1, 0. And we know this now because log of 1 is 0. So I know the graph is going to do something like this. Okay, but if you want to get more specific here, you've just got to think about values that you can easily take log of when your base is 3. So, like for instance, when x is 3, and you could even do a little table over here. We already know that the point 1, 0. Maybe I would tell you to plot 3 points. So plugging in a 3 in for x is easy. That's even one of our log properties. Log base 3 of 3 is 1. Okay, so then we could have that point. All right, what would be the next x value that would be easy to take log of when your base is 3? It would be 9, and that would give you 2. Okay, so this would be much further over up here, where this is 9, and that's 2. And there you go. Now we have a pretty accurate log graph that was not too bad to make. Okay, and your x values are going to change depending on what the base is. Now, if you want to do this in your calculator, though, okay, if you just type in log of x, it'll do log base 10 of x, which for the most part looks like the same graph. But if you want to do this more accurately in your calculator, you're going to have to, in y1, actually type in either log of x divided by log of 3, or natural log of x divided by natural log of 3. Oops. Okay, and I'm going to type in this one because I want you guys to get used to using natural log. Okay, so we would go into y equals, we would type in natural log of x divided by natural log of 3. Oops, not 6, 3. And I'm just going to do a zoom 6, and you're going to see this looks, this part of the graph is very steep right here, so it looks like it starts, it actually crosses, but we know that there's a vertical asymptote. This is, your calculator will only go so far. So if I want to be more accurate here, notice that there's the 9,2. What would be the next x value that would give me an integer y value? Hopefully you're thinking 27, because that's a power of 3. Basically it would be all the powers of 3. Alright. Okay, now let's do some actual solving for x. Okay, on some of these we're just going to work in exponents, and on some of these we're going to actually change them into logs. Okay, so this problem right here, if 7 were a power of 3, I could just get the same base on both sides and then set the exponents equal to each other. But I can't do that. Really, without a calculator, I can't even find my answer. But I can at least write an equivalent expression. Okay, so what we're going to do is we're going to take natural log of both sides. So I'm going to take natural log of 3 to the power of x plus 2. And that's going to be equal to natural log of 7. All right. Now, okay, sorry, just had a little interruption. Okay, and so from here we're going to use the log properties. This exponent is going to become the coefficient. So we're going to have x plus 2 now in front of natural log of 3, and we're multiplying now. X plus 2 times natural log of 3 equals natural log of 7. Now how would you isolate x plus 2? You would divide by natural log of 3. So then x plus 2 would become natural log of 7 divided by natural log of 3. And then you would subtract 2. So my exact answer would be x equals negative 2 plus natural log of 7 divided by natural log of 3. All right? And this is good. A lot of times this is all I'm going to want you to write. Now, if we want to actually find an approximate answer, we would just type this into the calculator. Okay? And you would just do it the way I showed you before. All right, real quick, I want to talk about alternate ways to solve this, because some of you might have been thinking, well, couldn't you have just done this or done this? And there are. I can think of at least 3 other ways to solve this. We could have, instead of doing natural log, taken log base 3 of both sides. And that would have simplified this side much simpler, because log base 3 of 3 would be 1, and then we'd just be left with x plus 2. We could have also written it from exponential to logarithmic, and I do want to at least write this down. What we could have done instead, and then some of you are going to like this a lot better, is we could have said, okay, this is the same as writing log base 3 of 7 equals the exponent, which is x plus 2, and then subtracted 2 from there. So what I want to ask you is, what is the difference in these 2 answers? Are they different, or do they just look different? Okay, they're the equivalent expressions. We know that log base 3 of 7 using change of base is natural log of 7 divided by natural log of 3. So either one of these would be fine for me. And obviously, if I asked for an approximate answer, you would type it into the calculator anyway. Truly, if I gave you a calculator, probably the easiest way to solve would, well, without doing, maybe not easiest, but the way that would get you out of any algebra would be to plug the graph of this into y1, plug the graph of this side into y2, and find the intersection. I want you to practice these algebra skills. I really don't want you to use the cheap way out. That would maybe be reserved just for checking your answer. Okay? So that's 4 different ways to solve your answer. Either one of these, either in blue or in red, are fine. I showed you this way in blue first because this is what you will see most likely in calculus. This is how they'll solve this problem. And so that's how I'm going to solve most of these in class. But I wanted you to see that you do have options. Okay. So now let's look at the next problem. So here we have e to the power of 3 minus 2x equals 4. And again, I am going to take natural log of both sides. All right, so then I have, natural log of e to the 3 minus 2x. This is actually just a property. You can change 3 minus 2x to being your coefficient and then say that natural log of e is 1, or you can just use the property that natural log of e to a power is that power. So 3 minus 2x is equal to natural log of 4. All right, and I would get the same expression if I converted this to a log, like how I did here in red. If I converted this to a log, just using the conversion, I would do log base e of 4 equals the exponent. Isn't that what the statement is? Natural log of 4 equals the exponent. Log base e is natural log. So I'm going to typically on these problems take natural log of both sides, but you can always just convert it to a log and then it'll put you in the same place. Okay. So we got to solve for x. So I'm going to subtract the 3. That gives me negative 2x equals natural log of 4 minus 3. A lot of times here, and in fact, I'm going to go ahead and erase it. Well, I'm not going to erase it, but a lot of times I'm going to put negative 3 first, just because if I'm going to type this in my calculator, I'm going to make sure that I'm not taking natural log of 4 minus 3, but natural log of 4 in the natural log, then minus 3. It doesn't really matter. There's no standard convention that you're going to see all the time. And plus, we're going to divide by negative 2 anyway. Okay, so that is my exact answer. If I'm asking you for an exact answer, it's this. If I'm asking you for an approximate answer, it means plug this into the calculator. Now, if you did plug this into the calculator, you would have to be careful about parentheses. This whole numerator, all right, and even the 4 would have to be in its own set of parentheses. And I'm not going to show you that right now. You guys know how to plug stuff into the calculator. Okay. Once you do get a number answer, sometimes the approximate answer is nice because it gives you an idea of really what x is. Like looking at this, it's hard to say. But you can always plug that value back in for x to check your answer. And like I said, you can always do a y1, a y2, and an intersection to find the value of x. That will only give you the approximate answer. If I want the exact answer, you have to go through all these algebraic steps. Okay, let's move on to the next one. This one's a little bit different. We're actually going to use u substitution here. What do you think we're going to let u be equal to? Okay, e to the x. All right, so then I'm going to have u squared minus u minus 6. Now this is a trinomial, and this is a quadratic, so I'm going to factor into u minus 3, u plus 2. You guys should be expert factors by now. Okay, so let's go ahead and solve for u. We've got one u value is equaling to 3, and one u value is equaling to negative 2. And this is not good enough because I didn't say solve for u, I said solve for x. So what we need to do is we need to do the substitution back. So now I have e to the x equals 3. And e to the x equaling negative 2. Okay, so then what does x equal here? It equals natural log of 3. And again, you can get this by converting into a log or taking natural log of both sides. And that looks like a good answer, and it's a pretty simple answer. Okay, over here, I end up getting x equals natural log of negative 2. This does not sit well with me. natural log only of positive numbers. Okay, that's the domain of natural log and log, all the logs. All right, so we're just going to cross this out. You can think of it kind of like an extraneous solution. It's not a solution though. And again, if I wanted the approximate answer, you'd actually type in natural log of 3 into your calculator. Okay. All right, let's, the next one is going to be very similar. We're also going to let u be equal to e to the x. Okay, so I'm going to have 3xu plus x squared u equals 0. Now obviously both of these were nice because they equaled 0. They didn't equal 0 and we knew we were probably going to have to factor. We'd have to make that happen, which we've already practiced in previous chapters. Okay, what can I factor out here? It's not a trinomial, but I can still factor out the greatest common factor, which is xu. And then you're left with 3 plus x. Okay, so it looks like I have 2 factors, but really I have 3. I have x, u, and 3 plus x. Okay, so because remember that this u is e to the x. Now if you feel like you can factor without doing u substitution, but just using e to the x, that's fine too. You don't have to do a u substitution, especially on a problem like this. So let's set our 3 factors equal to 0. We've got x equals to 0, and that's already solved for us. We've got e to the x is equal to 0, and that's going to change into natural log of 0. Sorry, x equals natural log of 0, which there's an asymptote there, so that's not a good solution either. You can only take log of positive numbers. All right, and then we've got 3 plus x is equal to 0, which gives us a solution of x equals negative 3. All right, at this point, since I'm getting actual numbers that I can plug in, this is a good time to bring up extraneous solutions. I kind of talked about it over here. These solutions were automatically taken out, but how could you check for extraneous solutions, or how do we check it? All right, we check it by plugging it back in and making sure that we can plug it back in. Now the nice thing about exponentials is their domain is all real numbers. So no matter what I have here, as long as I can actually do it, you know, we crossed off the ones we couldn't do, whatever number you get here, positive or negative, you can plug in for x. But what if your original problem has a log in it? Okay, that's when you're going to have to start checking for extraneous solutions. Okay, so we're going to see that next. All right, so on number 5, we have 4 plus 3 log 2x equals 10. Now I'm going to do some work, and what happens if I get a negative number for x? I have to take that out. It would be extraneous. I can only have positive values of what I'm taking log of. So in this case, x would have to be greater than 0. It couldn't even be 0. All right, it definitely couldn't be negative. Okay, so let's go ahead and solve this out. Let's think what would probably our first step would be to isolate the log. All right, so I'm going to subtract the 4. That's going to give me 3 log of 2x equal to 6. I'm going to divide by the 3. That's going to give me log of 2x equaling to 2. And now I have a log, and it's not obvious what the answer is right now, so I need to exponentiate. I need to write this as an exponent, okay? So what is the base of this log? It's 10, right? We can write that in. So 10 to the power of 2 is equal to 2x. Now this is a simple problem. It wasn't a second ago, now it is, and I can even figure it out. So then if 100 equals 2x, then x would be equal to 50. And 50 is okay to plug in. In fact, let's plug it in. 2 times 50 is 100. Log of 100 is 2. 2 times 3 is 6. 6 plus 4 is 10. We're all good to go. We even now know for sure our answer is right. Okay? So extraneous solution was not a problem on this one. This one looks more complicated. Looks like I might end up with a quadratic and multiple solutions, and we know that that's typically when we have extraneous, is when there's more than one solution. So here we don't just have to worry about x being negative, but even here plugging in a 1 in for x would be a problem, because 1 minus 1 is 0, and I can't take log of 0. That's not in the domain of logs. So let's just go ahead and go through the steps, and at the end we'll check for extraneous solutions. Okay, I have two logs. Okay, I can't isolate them separately. What I need to do is condense them into a single log, and I can do that because they are both common logs. They both have base 10. So what is the rule about adding logs? You would multiply their arguments. So here we have x plus 2 times x minus 1 equals 1. And so now I have a single log, and I'm going to do the same thing I did before. Whatever the base is, and if this had been natural log, I would use e, but it's the common log, which so I'm going to use 10. So I'm going to say 10 to the power of 1, and then that is going to equal this product right here, which I'm going to go ahead and multiply out to be x squared plus x minus 2. All right, now I have a quadratic. All right. I need to subtract the 10 over so that it equals 0. This is just a simple quadratic. Hopefully it factors, and if it doesn't factor, then we're going to be doing quadratic formula. Nice thing about this is that it does factor. So I've got x plus 4, x minus 3, and my solutions then would be x equals negative 4, x equals 3. You don't want to just automatically cancel out the negative. All right, you really need to think about it. Can x be negative 4? Well, no, because that's going to make me take log of a negative number. All right, there are circumstances, though, if I had turned this around and made it like 2 minus x, negative 4 would have been fine for this one. All right, so you don't want to just cross out negatives. You really do need to plug it back in. Okay, what about 3? Okay, just because 3 is positive doesn't mean it's good. You'd have to check it. Okay, it does end up being good here though, because 3 minus 1 is a positive number. Now this isn't as easy to calculate as the other one. You'd still have to use some log properties and go through it, but this does end up being a good solution. Okay, so definitely when your original problem has logs, you need to check for extraneous solutions. If this had been natural log, would I have gotten a number answer? No. Because you would have had an e here instead of a 10, and then that's going to be more complicated to solve. That's going to require a calculator, or we're going to have to do quadratic formula. It's going to get really messy. But on some other problems, it might not be so messy. Okay, so let's do a money problem. Let's end on a money problem. How long will it take $5,000 to double at 8.5% interest compounded quarterly? All right, this is something that people actually want to know. You want to say, when will I ever use this stuff? This is something that you might actually use in the very near future if you haven't already thought of things like this. Okay, here is the formula. Okay, we've already kind of talked about this. A is the final amount, P is the initial amount called the principal, R is the interest rate as a decimal, N is the number of times per year that the interest is compounded, and T is the number of years. So this is kind of like PERT, or the P-E-R-T, but that we use for continuously, and this is not continuously, this is quarterly. So we want to know how long will it take $5,000 to double. So for $5,000 to double, we're going to plug in 10,000, right? That's the doubling amount. And the initial amount was 5,000. We have 1 plus the rate is 0.085. Be really careful with this. If you get off on this, your whole answer is going to be weird. So be careful. Don't miss it because you just didn't move the decimal place over correctly. All right, quarterly, that would be 4 times per year. And this is going to be to the power of 4t because t is what I'm solving, how long. All right, solving this to estimate, or algebraically even, the first thing we would want to do is divide by 5,000. That's going to make this 2. So what I want to ask you is, did it matter that we knew how much we had in the beginning? It does not matter. Doubling time is doubling time no matter what you start with, which is good to know if you're thinking about investing money. Tripling, you could have just set a 3 right here. So in the future, you can maybe skip that first step and just go ahead and figure out what number should go here. All right, now if we're solving this out algebraically, this is an exponential. What would I do to solve? I would take natural log of both sides. So natural log of 2 equals natural log of, now this is going to be a decimal that you can actually I'm not going to simplify it, but you could actually figure out what number that is. You wouldn't want to round though, so I'm not even going to mess with that yet. All right, 4t is going to become my, 4t, 4t is going to become my coefficient here. And then I'm going to divide that natural log. So what ends up happening is I have natural log of 2 divided by natural log of 1 plus 0.085 divided by 4. That's going to equal 4t. So then how would you just find t? You would divide by 4, which would be like putting 4 down here. Okay, so let's type this into our calculator. All right, so we have natural log of 2. I'll wake up my calculator. I'm going to actually put all that in parentheses. Natural log of 2, that's the numerator, divided by the denominator of 4. I have natural log, and I have 1 plus 0.085 divided by 4. And there's your answer, 8.241 years. Okay, bring your questions to class.